right there on the title screen. Does the stream look okay? Do you hear me okay?
Yep.
Everything's good? Awesome. And then if you have questions during it, you can just throw it in the Computer Club's Discord channel. I have it up, so I should see it come in as I'm presenting. We can get going. People might pop in at like 35 or something, but that's okay. All right, welcome to one of our last meetings for the year. I think we have one more after this. I'm just going to talk a little bit about the evolution of crypto. I heard a beep. Okay, never mind. It was a good beep. So yeah, we're just going to talk a little bit about crypto today, and I'm not going to try and do like a crash course into the math and the meat of these crypto algorithms and stuff. I just kind of want to do this like high level overview, kind of introduce you to the concepts you're going to see in a crypto class, and yeah, stuff like that. So don't worry, you don't have to be good at math to understand what's going on here. So yeah. All right, so kind of the building blocks of crypto is just kind of, you can kind of break it down into these things. Modulo and inverses, and that builds primes in the GCD, or greatest common denominator, is kind of like the next step up. And then private and public info is kind of like the next step. It takes the previous concepts and then kind of adds an extra step. And then making it hard to brute force is kind of like the overall goal of algorithms, crypto algorithms. You want them to be difficult to brute force, so that way attackers can't read your messages. And I'll kind of explain each one of these a little bit more in depth. So modulo and inverse. You're going to first see these concepts in Math 201. It's the first time students are introduced to these concepts. And once you're done writing proofs in Math 201, because we all love to do that, you get to learn a little bit about kind of the early crypto concepts. So modulo, basically it just means remainders. So when you have division, it's if like 30 divided by 26. Typically we care about the 1 because that's the whole number that evenly divided it, blah, blah, blah. And sometimes we forget about the remainder, we forget about the decimal point. But modulo says, no, we should care about that remainder. And so, like I said, 30 divided by 26 is 1, remainder 4. Modulo is typically shown with the percent symbol. That's typically how you'll see it written, or if you're programming, that's typically the symbol that is used to indicate modulo in programming languages. So if you were to go into Python, C, chances are if you typed in, print out the answer to 30% sine 26, it should pop out 4, because that's typically how computers modulo. And the way you'll see it written in Math 201 typically is you're going to see 30 equals 4 mod 26, and mod's just short for modulo. So why do we care about these mod numbers? Well, we can take that mod, that 4, and we can turn it into a letter. So if we take mod 26, that means the numbers 0 through 25 are possible remainders, because the way division works, if you take something divided by 26, you can either have a 0 remainder, i.e. it divided perfectly, or you can have a remainder all the way up to 25. Because once you hit 26, then you're back to a 0 remainder and the process repeats. So that was one of the first things that kind of was crypto. Caesar cipher specifically, if you break down the math of the Caesar cipher, it's basically was this. It was mod 26, and when you shifted it, if it was a number above 26, that meant go back to the beginning of the alphabet, and mod just is what that math ended up being. Inverses are also a concept that you will be introduced to in Math 201. So basically, the point of inverses is if you can encrypt, you can decrypt. So one of the first encryption equations you're going to see is EX. I think it typically has a K subscript, but I couldn't figure out how to subscript in Google Slides. So 7x plus 14 equals mod 26. The plus 14 is your shift. 7x is the, I'm trying to think how it explains. The x is like the number or the letter that you are trying to encrypt. 14 is your shift, and then 7. I don't know how to explain this without going too in depth. Anyway, if you're dealing with, okay, I want to take this encryption function, and now I want to find the inverse of it. To find the decryption function, what you would do is move the 14 over, and you'd be left with 7x mod 26. And that 7, when you do multiplicative inverse, which is basically what times 7 is going to get you 1 mod 26. So 15 times 7 is 105. 105 divided by 26 is 4 remainder 1. So that means we just have this x by itself. When you do the inverse of it, that's what we want. We want the x by itself. Move the 15 back over, and minus 14. And then there's your decryption algorithm. It's a little bit, why the numbers do what they do is a little bit a little heavy in the math. And I'm trying not to go too heavy into the math, but trust me, that's how it works. Yeah. So the next kind of step in the evolution of crypto is we said, okay, so we have mod and we have inverses. That's cool. But what if we took it a step further by introducing primes and their inverses? So we like primes in crypto. They're very special because if you have a prime, that means you have an inverse. And 2 primes, if they have a GCD of 1, greatest common divisor denominator, that means an inverse exists. And if we have a GCD of 1, encryption algorithms really like that. That means good things that we can use this to it's kind of like when you're running like a big thing of numbers, that GCD equals 1 is going to stick out because it's like the only not weird thing, because like all the other numbers are going to look weird or outputs are going to be weird. So then you see that, and that's good. So the first time you're going to kind of see this concept is when you're in Math 201 and Spanier or Wickline or whoever you're taking it with tells you about, today we're learning about the Euclidean algorithm, an extended Euclidean algorithm. And they work with the GCD equals 1. And basically what you do is you have these 2 primes and you work through this method. And it's multiple steps. And eventually you get down to more or less everything equaling 1. And it's super nice and super slick. And you're going to have to do it by hand. And then eventually they'll give you programming code to do it, which is nice of them. And the extended Euclidean is basically doing that backwards. And it can help you find the primes you originally started with, which is something attackers like. And it's also something that crypto algorithms like, because that means, oh, I can solve this and I can decrypt. And something else that's interesting about primes is as you head towards infinity, primes get rarer and rarer. So when you're looking at encryption algorithms and you have to pick out 2 primes, an example of an algorithm that does that. Let's say Diffie-Hellman, but we'll talk about that one in the next slide. You have to pick out primes that are large because computers have a tough time brute forcing large numbers. We'll talk about that a little bit. And like I said, as you get towards infinite, primes get more and more rare, and computers are going to take a longer time to find the primes that you used. So when you're using an algorithm, if you're somehow doing it by hand, it's in your best interest to do these bigger numbers, because computers are going to have a hard time decrypting your stuff. So GCDs, primes, we like them because they give us these special answers, this special output that tips us off to like, yep, there's the answer, there's solution. We can use this to decrypt. These are the numbers we have to use, more or less. So the next kind of evolution in the chain was, it was like, cool, we have this math and it involves mod, and we're using primes mostly to generate these numbers that we're sending off. But what's bad is that the attackers, they're seeing all of the math we're doing. That doesn't make sense, because if you're sending it over a public channel and you're sending, like, this is all my numbers and my math, and if the person you're intending you want to see it sees it, well, someone else could see it too. So it's not really secure. So Diffie-Hellman, RSA, the AES, kind of, Diffie-Hellman was the first big encryption system that decided to use keys. So we have these private key, we have public keys. Asymmetric, symmetric could deal with it too. So you don't get into this stuff until Math 436, which is number theory and cryptography, I think. And basically what it boils down to is Alice generates a key using information only she knows. She has these 2 primes that she's going to keep secret. She does some math and comes up with this one big number, and she sends it to Bob. And Bob says, okay, cool. And he uses his own private information and a private message, and he scrambles it all together. So he he scrambles Alice's key, his private information, and private message. All gets scrambled up. He sends it to Alice, and Alice, if you follow the math, which it's a pain in the butt to look at times, she can decrypt it on her end using her private information, and it's great because she can verify. There's also a nice trick where she can like verify that Bob is telling the truth and like he didn't do anything weird to it. If she maybe believes that he sent her some weird information, like if they were arguing or doing like a coin flip through some message service, she can use the numbers on her end and have Bob send her some numbers, and she can kind of like check the math and make sure Bob wasn't lying, which is really nice. And she can also use it. Digital signatures are also an example of this, using these kind of public-private keys, making sure that things didn't get tampered with. Yeah, so that was like the next evolution, and we were like, yeah, this is great. Why wouldn't we do this? Why weren't we doing this before? And when you look at the math inside of these keys, we're using mod. It's like this whole math equation with tons of variables, mod Q. And Q is just a stand-in for a large number that Alice has. And it's using inverses because you have all these variables, and if you look at it, you can gotta go, wait a minute, this cancels with this, and this has an inverse, so that cancels that, and you're left with this super slick, easy, the message, more or less, which is really nice. So the next overall thing that we kind of realized was, okay, we've got this public key, private key. This is really nice. And attackers started to come in and go, wait a minute. I know how this math works because the math got published. We couldn't not publish it in papers, right? The attackers started looking at like, wait a minute, I know how the math works, and I just don't know what exact numbers were used. And I know I need to find an inverse. I know I need to look for primes. So why don't I just start brute forcing it? And eventually I'll get the answer, and I'll find the message, or I'll find the primes that were used. When Alice generated her key, then I'll have her private key, and I'll use that to read the messages from Bob. So it became this thing of, wait a minute, we need to start changing how we do this. We can't use small numbers. So in Math 436, you're going to use smaller numbers. That's just because for the sake of the concept, for writing it out in class and understanding it, it's going to use small numbers. But in the real world, you're going to use larger numbers. So basically what we're saying is we got to use these large numbers in these crypto systems. We got to use large primes. So it takes a long time for your standard computer crack the math. And if a computer cracks the math, it means we're screwed. We got to come up with something else. And, nowadays I think we use pretty good numbers. They're large, hard to break. The math behind current systems is kind of hard for computers to like do really, really fast. So right now, we're kind of at this nice spot of like, yeah, we've kind of got this figured out, and we're not too worried. Modern computers kind of struggle with cracking our current systems. But, there's the big but, what about quantum computers? Quantum computers are going to be insanely fast. They're going to be able to crack our current systems very quickly, very easily, even if we have really big numbers with complex math. So everyone just kind of started looking around, scratching their heads like, okay, we got to be proactive about this. We can't keep using RSA, AES, Diffie-Hellman, when quantum computers become more mainstream and accessible to the public, i.e. attackers. So what are we going to do? NIST wants to know the answer to this question as well. So NIST actually has a project currently going on. They call it the Post-Quantum Cryptography Project. They basically to the international group. Basically, we want to know next crypto use in a and and computer to NIST that that should be the standard encryption algorithm we're going to use. And weirdly enough, some people kind of actually did like joke submissions. So if you didn't think mathematicians had a sense of humor, you're wrong. They were like sending like these super, they were sending in like RSA, AES, just because they were like, I mean, if it ain't broke, don't fix it. But those got knocked out pretty quick. The project is currently in round 3. So they've had 3 rounds of, they accepted submissions, and then they've had people go in and check the math, check how efficient the algorithms are, because that's the big thing is like, they have to be tough to crack, but they also need to be efficient. Because if it takes 20 minutes for your algorithm to run, no one's going to want to use it to encrypt. Unless, I don't know, maybe some like top secret government thing that doesn't care about speed. So like all of federal government, I guess. But anyway, yeah, this is a really cool project, and I think, I'm not sure when they're going to be done with round 3, but they are in comment period. So if you want to go check it out and check out the different submissions, and each one has like a website, they can read up about them more, which is pretty interesting. So right now we have 4 contenders for our next, the next big standard. So we have the classic, I'm sure we could say it, McLEC. That one, weirdly enough, didn't have a website. I don't know why they didn't. I think it was just a paper. Or no, it had a website. I think it did. And then you could also read the paper. There's also one called Crystal Cyber. And this one uses a form of encryption called lattices. So the idea is that you have this number and you have kind of like a diamond shape drawn on a graph, and you want to find the shortest vector. So you want to find the dot that's closest to your first dot, if that makes sense. Ntrue is one that Math 437 focused on heavily. We actually just got done learning about that one. And it seems pretty strong. I don't know if it'll win, but I guess I'm kind of biased because it was the only one I learned about. And then Saber is also the next one. These are all, they've made it to round 3, so they're all pretty good, pretty strong. There's also a digital signature algorithm section of the competition. I call it a competition. It's not really, because even if these, say NIST and all the mathematicians, I'm sure they've pulled in to help them research these and study these and make sure they're up to snuff. If the math and the facts come back saying, hey, both of these are, crystals and Ntrue are the best too, then we're going to make both of these the next standard for, quantum computing. That this is what we're going to use. We're going to use both of them. So it's not just we only get one pick, winner takes all. It might be possible we use all 4 in a post-quantum world. I just don't really know. They're still doing the math, still checking on it to making sure it really is as strong as the authors and the people that came up with the system claim it to be. So they've been scrutinizing it really hard. They've had attackers going in and trying to figure out how can we really mess with it and get decrypt messages and stuff like that. So yeah, it's definitely something interesting going on in the crypto world. Good idea to keep an eye on it. So overall, math in crypto has gotten more complicated, and the numbers that we use have gotten bigger because computers have gotten faster and better at cracking bad math. It used to be where we just had, mod 26, because there was 26 letters in the alphabet, and that's really all we needed. And then we started to realize, no, we got to use different numbers. We got to use better numbers. That's where primes came in. And then after that, it was like, okay, we got to hide our numbers from the attackers. And just kind of kept building on it because computers just kept getting better. And they were just really good at cracking the math that these algorithms used. And we've always used our previous encryption methods to build and improve the next one. So basically, we took the good stuff of these algorithms and left the bad stuff behind. We left the math that was easy for a computer to run through quickly. We left that behind. We used more complicated math. We left behind the idea of only using 0 through 25. We started using primes. So yeah, it just kept building. And overall, crypto is going to continue to evolve. It's always going to change, and we're always going to need to be building the next system, the next evolution of it. Because as soon as we get an encryption crypto algorithm, chances are there's already people out there trying to crack it, trying to break it, trying to find ways to make it do weird things that mathematicians didn't originally intend for it to do. All of a sudden, we might find this weird way of like, yeah, if you, fill it with a bunch of zeros, it breaks, or, make it too large and it breaks. That's something that has happened with Andrew, is if you add too many numbers, then things start to fall apart on you. So each crypto system is going to have its faults, and we need to, in the next system, fix those, make something better. And we've just kind of overall have just made the math more complex, harder, and we've just added more variables, or we've added these kind of weird, funky things that math has, or that we find. Add that into crypto. Computers configured can do it quickly, but if you don't know the numbers originally, if you got to brute force it, it's going to take you a long time. So it's kind of this weird catch-22 of computers. But basically, if you're really big into crypto, good news, you're going to have a job because we're going to need mathematicians that are working on the next crypto system. We're going to constantly need people to do that. We're going to constantly need people to program computers to make sure this works and to do trials of it. And on the attacker side of things, we're going to need people to break the systems. We need people that have a strong math background that can look at these crypto systems and say, okay, how can I break this? And because we need to know how to the benefits and the drawbacks of each crypto system. We need to know where the vulnerabilities are. We need to know that this has a weird problem, and if an attacker can somehow use this to their advantage, they can break the system. They can break this encryption algorithm. That's bad. So we need people with a math background and a cybersecurity background to really test the strength of the encryption algorithms we come up with. Because, mathematicians, they can make them, but we need hackers to break them. So, yeah. That's pretty much it. Do we have any questions? free to say them out loud or pop them in the computer club chat. No? Okay. But yeah, we're gonna have one more meeting this semester, and then we'll be off for break, Thanksgiving break, and then that next week is finals, and then Christmas break. So it's been a great semester so far, and we hope to end it with on a high note next week. I think we were gonna do Jeopardy or some sort of Kahoot. I think it was just gonna be over generic stuff. I'm not sure exactly what the plan is yet. But yeah, that's kind of the idea. So we hope to see you all there. And don't forget to fill out attendance if you didn't already. And yeah, just have a good week, everybody.
Thanks, you too.
Stop stream. If I can find the button.